I have another computer I can check, just to be sure. It says starting preview, so I want to make sure we actually are live. And let's go, let's see. Come on. Is it going? Yes, wonderful. Okay, great. I will close this. Well, or minimize it here. Put that right like that. And I know I'm supposed to wait about 30 seconds for people to join. I hope you all can hear me. This is my third live video course I've been doing. And it's wonderful. I'm using my new equipment again, and hopefully things will be a little bit better this time than before. I will probably wait to see whether or not you guys actually have sound. I want to make sure everybody can hear me. Come on, get back up. Let's see. Why isn't this working? Sorry guys, hang on with me. Let me go to YouTube so I can actually see the chat. Do we have people in the chat? Hi everyone. Okay, great. Hi guys. Okay, you can see me. Wonderful. Thank you. Can you hear me all right? Can everybody hear me? I have my sound down here, so I want to make sure that I sound good. I'm not distorted. I'm still working out the bugs in the new equipment, so I want to make sure that it's all good. So let me know when you can. And I'm not seeing. I'm so used to Periscope, which is got like this instant feedback, and this is all delayed. Okay, good. See me loud and clear. Thank you so much. Okay, that helps me. Wonderful. And I will now hide this so we don't get confused here. Okay, my name is Dr. Tamitha Scove, and I am a space plasma physicist. And basically what that means is that I do space weather for a living. And it's a lot of fun. And recently I've joined Patreon to allow myself really what you guys have all asked me to do, which is to teach more courses and do more educational content and help everybody understand what space weather is, and also to try to bring space weather to terrestrial meteorology and educate just typical weather people on what space weather is and why it's so important, and why it really, for the modern meteorologist, it's becoming the weather of the 21st century. And so my goal, ultimate goal, is to get space weather on the 6 o'clock news. And I'm working towards it, and we're actually starting to do training courses to make that happen. And by doing these mini courses, it also allows me to educate you guys on this new kind of weather. And I have up here, I have all the patrons who are actually sponsoring this this particular course, and I thank you so much. I've got my steering committee here, and then I've got all the mini course patrons. You guys are just so important to me. I am so very grateful. And because of all of your support, I have actually created a slightly more formal method this time. And so we're going to try this out, because this is only the third time I've done these courses. Everything is still kind of in flux. So definitely let me know what you think. If you like this new format, it's a little bit more written. I've got text boxes. You'll see. It's stuff that's a little bit more formalized, what you would actually do in a real classroom. So let me know if you like that. And I will be stopping several times during the course to check the chat and try to answer questions. And then I, again, at the very end of the course, will do the same and check the questions again and see what everybody thinks, and if they've got follow-up questions and all that kind of stuff. So the title of this is Sunspots and Telescopes. This was chosen by all of these people here. The subject is really kind of a follow-on from one of the last courses I did, where people were asking a lot of questions about plasmas and how does the sun work and why are sunspots important and how come I get confusing information about really what sunspots are and whether they're bright or they're dim or they're noisy. And so I wanted to try to fill in some of those gaps for you. So I put this course together so that we can really talk about that. And without further ado, I will begin. Okay. Now this is our star, and I have to start this way because we're really going to be talking a lot about the solar dynamo. And this is one thing that I will always say that distinguishes a space weather scientist from, let's say, an astronomer. Now you can be a solar astronomer and you know, and study the sun and study the interior of the sun and all that kind of stuff. But really, the sun, to most astronomers, the sun is pretty boring. It's not all that big. I mean, here's our sun here compared to Arcturus. It's really not that exciting in terms of how rare it is. I mean, you can have hot blue stars and bright stars, 1 in 30,000 or 1 in 1,000. Our star isn't even close to 1 in 100. Our star is a G-type star, and it's only 1 in 15. So pretty much anywhere you look in the universe, you'll find a star just like ours, and oftentimes much bigger than ours. So really, astronomers, most of them anyway, kind of look at our stars, you know, yawn material. But they don't look at the star the same way we do. You know, us space weather people, we look at the star not because of the type of star it is, but because of what it throws at us and how it throws at us what it does. So for us, a very boring star suddenly becomes very fascinating. And that's what you'll see some of that today. But to start, I need to kind of show you that, you know, our star, it's not like you cut it open and it's all the same on the inside. There are so many different layers going on inside our star, and we kind of have to learn how to understand all of them as best as possible. You've got an inner core. As a matter of fact, I think I can go to the next slide where I talk about it more. This is that same picture I just showed you, but I've also broken it down. This is actually Alex Young's picture I took from the sun today. He's got a nice little cutout that kind of shows some of the ways we observe the star as well, instead of just having that cutout. But the sun basically can be divided into 6 layers. We've got the core. You can kind of see it here and right in here. This is the interior. This is the hottest part of our star. It's 28 million degrees Fahrenheit, or what, about 15, almost 16 million degrees Kelvin. I shouldn't say degrees Kelvin. I just call it Kelvin. There's no degrees. Once you move out, and this takes up quite a bit of our star, once you move outward a little bit, you get to the radiative zone. And they call it, they show it here kind of as a color code because it's not exactly even. We don't know a lot about the interior of the sun, nearly as much as we'd like. It's very hard to peer into it. But the radiative zone, this is where basically you just have emission of light. It's all bouncing around like crazy. As a matter of fact, because the plasma is so dense in there, you can actually have light waves bouncing around for 100,000 years before they finally escape, because there's just so many collisions that are going on all the time. It's almost impossible to get the light to get out at any decent length of time. Once you get past the radiative zone, let's say it takes 100,000 years and now you finally got past it, now everything changes, because the plasma that was there, and I'll talk about a plasma in a second because it's very important to what we're doing. Once you get past that radiative zone, the plasma is, it's not as dense as it was. And on top of that, it now has, it doesn't have all the electrons stripped off. It actually can absorb some of that radiative energy. So what happens now is that now you get currents. You get currents and you get bubbling and you get what looks on the surface as granules. You have supergranules and other granules. It's like a pot of boiling water all the time. And what's cool about that is that that's actually part of the network that creates bright spots and dim spots, and we'll talk a little bit about that shortly. But once you get past the convective zone, and this is also where the solar dynamo is created, and we'll talk very much about that because that's critical for sunspots. Once you get past that, then you get to the photosphere. Now the photosphere is basically what we call the visible surface of the sun. It's about 10,000 degrees Fahrenheit. This is what you see essentially when you look through telescopes on the ground and you see your yellow sun. You see that, and that's where the surface, that's where sunspots actually appear to the naked eye. Then you get up, you're starting to get up even further out. Now you're leaving the surface of the sun, you're now above the sun, and you're going into a transition region where you're beginning to transition into the solar atmosphere. And this is called the chromosphere. It's a very, very dynamic layer, and it's very thin, but this is where a lot of the solar storms are born, because there's just so much going on in that region and it's very unstable. But it makes it incredibly fascinating for space weather scientists. And then, of course, once you transition into the solar atmosphere, you're in the corona, and it's very hot again. 3.6 million degrees Fahrenheit, much hotter than the surface of the sun, as you can see. And that's part of the reason why the chromosphere is so dynamic, is that everything is heating again. So it's a very, and we don't even really understand this yet. We have a lot of theories, and that's one of the reasons why the Parker Solar Probe has been launched. We're trying so desperately to solve this dilemma. But we need observations, and we need observations close to the sun. We need to get through all this space so that we can see the sun from close up, and we can get close to really sampling that corona, if not what some people consider actually sampling the corona of our star and trying to get really into the nuts and bolts of things. It's hard to understand something when you can only look at it from a long distance away. So that's the neat thing about being a space weather scientist, is that we get a chance to actually go to the places that we're looking at and sample what their atmospheres and what their planets are like. So it helps us immensely when we're trying to create models of how things work. And the sun is very much still a mystery to us. So let me talk a little bit about this. This is a direct question that we got from one of our Patreon members. As, okay, everybody talks about plasmas. What is a plasma? Why is it important? Why do magnetic fields matter to a plasma but not to a gas? Okay, let's see if I can help explain this. Plasmas, we talk about plasmas so incredibly often because really they're the fourth state of matter. You know, I'm sure you're used to solid, liquid, and gas. We all kind of know, and we're using the example of water, right? Ice, water, and steam. And in ice, of course, it's a solid, so the atoms are very closely locked, and they don't really move. It's a very rigid structure. In water, well, they're still very close together, but now they kind of slide across each other, and they take the shape of whatever container you put them in, right? Water doesn't care what shape it is, whereas ice does. And then if you go to steam, you heat it up or you vaporize it somehow. Well, now there's a lot more energy, and these particles separate even more. And now they'll fill up an entire container. They won't even really be as affected by gravity and have to stay at the bottom of the container. They'll fill it completely up. And obviously with clouds, they can take pretty much any formation they want. But what happens when you go past this? What do? Well, let's decide that instead of just keeping everything neutral, because that's what we've got here. These are all neutral atoms or neutral molecules. In this case, let's ionize them. Let's strip off some electrons and just rip it apart a little bit. Now you've got molecules that are positively charged, and you've got electrons negatively charged. Well, now you've already created some kind of electric potential. And as soon as you create that, as soon as you get into that aspect of how molecules and atoms and elements work, well, now you're talking electric fields as well as magnetic fields. Because now, electricity and magnetism go hand in hand. You almost can't talk about one without another. As soon as you move an electric field, magnetic fields are going to be there whether you like it or not. You can't really have much in the way of electrodynamics, as we call it, without invoking magnetic fields. So, and vice versa. So, and if anyone wants to know the details of that, just look up Maxwell's laws, and you'll see a lot of chicken scratch and crazy nomenclature, but those are the laws that really dominate when it comes to electricity and magnetism. So let's go ahead and strip off electrons and make these things positive and negative. So in an ionized gas, in this case, we've only stripped off some of them. We've got positive charges here, negative charges here. There's some free electrons floating around. Okay, so these are ions, positive and negative ions, and then electrons, as well as some neutral stuff. Now, where do you see that in life? Well, lightning. Lightning's a classic example. And of course, what is it? It's electricity, right? You know where else you see it? Neon beer sign, right? A big Budweiser sign or a big glowing neon sign, or the mercury lamps that you have at the ceiling in your office. Those are all plasmas, believe it or not. But they're not space plasmas. They're collisional plasmas. That's one of the reasons why lightning, if you notice, it's all scraggly, right? Lightning doesn't look anything like aurora, yet aurora is also a plasma. Now, why is that? Why doesn't aurora look more like lightning? And the funny thing is, I have been asking people, I've been waiting really, for people to ask me that, for somebody out there to ask me, well, if aurora is a plasma and aurora is lit up is because it's a plasma, and lightning is a plasma, why do they look so fundamentally different? And the reason is because this is a collisional plasma. What happens when you take most of the particles out, right? Here, the particles can bump into each other. They can talk to each other directly by smashing into one another, okay? And that causes a lot of the jagged lines that you see. But when you go into space, when you take most of those particles away, when you go into a vacuum, most of the particles are gone. And now, they don't really touch each other anymore. But just because they can't touch each other doesn't mean they don't communicate. They do. But they're communicating now solely through their electric and magnetic fields. This is what we call a collisionless plasma. So I've seen, I think it might have actually been Ben Davidson had a plasma experiment or something, and he showed how it was all, he was lighting up a plasma in a tube, and it was very ratty. It looked very much like lightning. It was very jagged and stochastic, crazy stuff, because it was being bombarded. There were all these particles in there being bombarded. And he says, watch what happens when I turn the vacuum up. And he says, we evacuate it and make it like space. And suddenly the plasma smoothed out. And it was all suddenly very fluid and looking very, very pretty and smooth, just like aurora. And the funny thing is that he never talked about why that happened. He just kind of glossed over it, saying, well, this is just the way it works in space. Well, this is why it works like this in space. Because when you have a collisional plasma, you still have so many collisions that is the force that dominates. It dominates the movement, it dominates the direction the plasma moves, it dominates everything. But when you have a collisionless plasma, now you don't worry about it. It's almost as if all the particles are connected by a spider web. So if you jiggle a particle over here, a particle over there wiggles. You push like this with the magnetic field, and a particle over there feels that push and goes boof. Okay? So this is how a collisionless plasma works. This is how it works in space. And we've got both of these types of plasmas in the sun. We've got collisional plasmas and collisionless plasmas. So it's very, very, very complicated, but as you can see already, the biggest difference between a gas and a plasma is that you add the electric and magnetic fields, and these forces can take over. The more that that plasma becomes collisionless and vacuous, the more the electric fields and the magnetic fields, these invisible lines of force, those dominate the movement, the communication between particles. And that's why you hear me talk so much about magnetic fields and electric fields in the sun. So hopefully that helps settle some of that. I will go back a little bit later and see if you guys have more questions on that. But now let me move to the discussion of how sunspots form. So now that we know that magnetic fields, and by inference electric fields as well, that we know why we know that how important they are in the sun, let's talk a little bit about how sunspots form. So if we talk, hopefully you can see this. This is the sun here. It kind of looks like it cut off this edge. This says field lines. Okay, so this is, let's do this 1, 2, 3-step process. This is a very famous image, by the way, from UCAR. I used it because I love how it's been annotated. It really kind of helps. But UCAR has some really nice basic information on the solar dynamo, and this is part of that. So let's take some magnetic field lines at the sun, and let's draw them from south to north. I believe that's the way we're doing it. And the neat thing about the sun, and this is kind of like the way just a normal dipole magnet works. You've got field lines that go, one direction through the pole, and then they come back out and loop. Okay, that's just a typical dipole. We're doing something very simple. But this is not a rigid body. This is rotating. And the one thing that Galileo recognized early on was that he watched sunspots rotating across the sun, and he said, huh, isn't that strange? Sunspots rotate slower across high latitude parts of the sun and faster across low latitude parts near the equator. And it led him to believe that the sun, even though it rotates, and we know it rotates relative to the Earth about 27 days, give or take, in an inertial state, it's from a fixed point in space, not moving with the Earth, it takes about 24 days. It's faster because the Earth kind of chases the sun on the way, on its rotation. so it looks slower from Earth's point of view. But even though we consider that to be about the sun's rotation rate, it doesn't rotate the same speed all the way across from high latitudes to low latitudes. It actually rotates faster in the middle. We call this differential rotation. And so what happens is if you take field lines that are locked into the plasma, because when you have electric fields and magnetic fields with charged particles, it jails those particles. They have to respond to the magnetic field. So you can almost look at these lines as if they were literally bars, jail bars. And these particles actually just have to spiral around them a lot of the time. They're not just free to move wherever they want to, because when they try to, the magnetic field or the forces suck it right back around that particular field line. So they just kind of gyrate around and up and down and bounce and stuff, but they're locked. So as you take these magnetic field lines and you look at them, if the sun is rotating faster at the equator, these lines are suddenly going to move because the magnetic field is also locked. The particles in the field move together. We call that frozen in flux. And they're locked together. And so you're going to get the field lines bending. And as you get one rotation, you kind of get a little bit of a bend. You get multiple rotations, it bends even more because now you're stretching these field lines around the equator much faster than you're stretching them at the poles. Okay, so pretty soon you get a picture that looks like this, where you're just, literally winding this thing up, rotation after rotation after rotation. Well, eventually, because you can actually, there really is no tension on field lines. It's not like guitar strings. You can stretch magnetic field lines forever. They don't care. What they don't like to be is bent. That's a problem for them. But stretching them, that's okay. But when you do stretch them, sometimes they'll break, or because of the buoyancy, they'll begin to lift up, and they'll pop out of the surface of the sun. And when they pop out, they actually pop out and form these big loops, right? But then you've got a south pole and a north pole because they're still connected to each other. And down on the other side, you would get it the opposite direction. You get a north leading and a south leading and a north trailing. Here it's a north leading and a south trailing because you're on other sides of the hemisphere. But yeah, there's all sorts of like buoyant forces and things that are going on inside the sun that we don't understand all that well. But those forces help lift these long stretched field lines right up to the surface and pop them out, especially if they're strong, if they're magnetically strong. Let's see. Yeah, okay, I think I went through that. And here's a little bit more detail for you. We call this the omega effect, where here's poloidal field lines, as we're calling them. Here's the axis spinning. You get that differential rotation again, and after many, many, many rotations, you actually can turn a field that goes straight up and down into a field that's almost completely sideways. So you can take poloidal field and turn it into toroidal field. And now these things are popping out. Again, these lines will lift up and be buoyant, and they'll reach the surface of the sun and pop out and create sunspots on the sun. And we'll talk more about the details. There's also another effect called the alpha effect. Okay? And all of this is part of the solar dynamo. The alpha effect we don't understand quite so well. We're working on it. But it's really hard to understand because some parts of the sun are not visible to us. And the convection zone some of it's a bit of a mystery. But we get twisting of the field lines. Part of this has to do with buoyancy, but part of this has to do with some other forces. You can get magnetic loops, and somehow, magic happens, and we restore the poloidal field, and that's how we start a new cycle. So you start a sun cycle with poloidal field pointing one direction, and then it twists up and to the point where it gets completely unrecognizable. You get all this twisting of field, reconnection, all sorts of things, bubbles, all sorts of stuff happens, and it recreates this poloidal field, and it points the opposite direction, which is when the sun pole flips. Okay, so all of this we believe in kind of a nutshell is how the dynamo works. And I'm sure I'm going to get some solar physicists saying, "Oh, boy, you said that wrong." Maybe I did. Hopefully that's close enough for this kind of thing. But this is a very complicated process, and we don't have all the answers yet. But it is all part of this solar dynamo, and let me see if I can help you put it together in a slightly tighter package. So, how does this affect sunspots? Why why are we thinking solar dynamo? Okay, I get it that it pops sunspots out of the sun. What you've got to think of is that this field, now recognize this is that field being stretched around the equator, okay, and this is a cutout of the sun. We're stretched out around the equator, but those field lines that are being stretched are in the convection zone. They're not on the surface of the sun. They're deeper in. Remember the layers? They're deeper inside. Here is the convection zone, essentially, and really we have currents. This is part of what we think helps restore that poloidal field. These are the way some of the convection zone, or the current patterns in the convection zone work. Now notice, the field that we're talking about, is actually deep in the convection zone. So you're getting these field lines twisted up, right? And you're getting sunspots with buoyant forces popping out on the surface of the sun, which is higher than the field lines are. You can kind of see some of the field lines in here, hopefully. There's kind of a shadow. They're just trying to show you what's under the surface. You can see the sunspot there, and you can see this big magnetic loop coming out, right? But the thing is that these sunspots don't just pop out willy-nilly. What happens with this convection, do you see how this pattern right where the field lines are is going down toward the equator? Aha, that should tell you something. What happens is that as these field lines begin to twist, where you get the popping out first is up at higher latitudes. And guess what? Anyone who's ever seen a butterfly diagram knows that solar cycles start right about here. This is 60, 70, 80, 1990 on up. We've hidden part of it. But this is the beginning of a sunspot cycle right here. And then the sunspots kind of go down. This is in latitude, high latitude up here, equator here, high latitude again in the southern side. So you can see sunspots over time start at high latitude, both north and south, and then they travel, as they begin to appear, they appear lower and lower and lower and lower and lower in latitude until eventually they stop and the new cycle begins. And what happens? You've got sunspots appearing with the new cycle with reversed polarity at high latitudes again. And that's due to this, we think. What you see is that the sunspots pop here, but as this current continues to drive downwards, you get these sunspots coming in lower and lower and lower and lower latitudes until they get right there. And by that time, the magnetic field is so jumbled and twisted that it's actually recreating the poloidal field again somehow. And again, we might have to enlist an actual solar physicist, which I am not, to be able to talk about that, because that's a bit beyond my expertise. Remember, my expertise is not solar physics. I am not a solar astronomer, but I'm a space weather physicist. So forgive me if I've done a few things that might be slightly glossing over some of the details, but we can, I'll be sure to answer your questions, and if there are ones that I can't answer, I will find the answer for you from talking to people who have the right expertise. But at any rate, so hopefully this gives you kind of a better idea of how the picture works. Sunspots pop up out of the surface because of some processes that are going on far deeper inside the sun, right? Now here's the interesting thing. If anyone knows about the Earth's magnetic core, right, we think that our magnetic shield and our dynamo, our Earth's dynamo, magnetic dynamo, is created by our iron core, right, which is at the center of Earth. Here, this core, this solar dynamo, is actually being created in the convection zone, not in the inner core. So that's one of the cool things about the sun, is that we don't believe that the sun's dynamo is actually being created at the center of the sun, like it is at Earth. It's actually being created much further up, which makes the sun incredibly fascinating, but also a bit frustrating, because it doesn't like to let go of its secrets very easily. So hopefully that answers that. And let me see if this is a good place. Yes, before I go into the details of sunspots, let me stop for a second and see if I can answer any questions you might have. Do I have any questions here? When I was young, the weather girl fascinated, especially her outfits. Well, I'm not a great dresser, so let's see. I was told our eyes have less sensitivity to green because green wavelengths pass through the upper atmosphere the strongest, so our sun is actually tinted green. Actually, I did not include, a brightness, an irradiance chart that shows actually the spectral radiance of the sun. But it actually does peak in yellow. So and it's very fascinating because I've had multiple discussions with medical professionals who say, well, obviously that's why our skin is kind of tinted different shades of brown. We're not Avatar. We don't have Avatar skin because and be blue because our sun isn't blue. Our sun is yellow, and this is about as close to yellow as we get in terms of our skin tone because it's trying to protect us to some degree from and that's why melanin is the color it is because we have a yellow star. If we were on a different planet, or I mean within a different star system with a different colored star, there's a very good chance our skin would not be this color. And I thought, how fascinating, what a neat idea, that because we have a bright yellow star, it dictates the color of our skin. So anybody who's racist, that should blow any of their theories right out the window, because the reason why we are the colors that we are is because of our star, not because of culture or anything else. I think it's really neat, a neat way of kind of humanizing everything and just normalizing it based on the universe. And anyway, that's too philosophical, I'm sure, but that was an interesting question. So yes, our eyes, I think, are a bit more sensitive to that's why our eyes see in the visible range, definitely. But there may be some reason why we see a little bit better in green and yellow, because that's going to be where the sun peaks in its brightness. Okay, any other questions? Let's see. Cell circulations of Earth atmosphere being similar. Hadley's cell. I don't know about Hadley's cell. I need to learn more about meteorology. And I will, I promise. That's on my list of things to do. So I can't tell you about Hadley cells, but I can tell you, if you talk to Dr. Scott McIntosh about Rossby waves, we see those all the time in the atmosphere at Earth. And as a matter of fact, a terrestrial meteorologist helped him identify Rossby waves on the sun. That does seem to drive some of this dynamic. So this was a very good question. It does seem to drive some of the dynamics of when we see sunspots. What helps the buoyant forces pop these magnetic field loops up through the surface of the sun. It looks like Rossby waves play a role. And so when we see sunspots on the sun, they cluster. And what happens is that as the sun rotates, you can see almost on the same location, the sun will rotate and you'll see sunspots form as it passes over some really turbulent area deeper inside. And the sunspots will form, they'll grow, and then they'll kind of decay. And new parts of the sun will rotate, and new sunspots will form right over that same region, as if there was something underneath bubbling up and creating waves that are lifting the magnetic field loops right through the surface of the sun at that location. It's kind of like like an underwater volcano or something that is pushing the stuff up at the same location inside, deep inside the sun. So these are really pioneering areas of solar physics. And yes, we are seeing some similarities between what goes on at Earth in the upper atmosphere and what is happening on the sun, deep inside the sun itself. It's very fascinating, but there's not a lot of connection yet between terrestrial meteorology and solar physics. So let's see, any other questions? I don't see any new questions yet. That may be just because I may be slow on the uptake here. Just because I'm streaming. So let me get back to this. Okay, so we talked about sunspots, how they're forming. Let's talk a little bit about why we get the colors we get. Now, you'll already see that this graphic is wrong. You're already smarter than the person who put this together. Hot gas. Is this a gas? Gas? Really? Come on. A plasma is not hard to understand. It's just a gas that's magnetized. It's got electric and magnetic fields. It's got electric charges in there. This is not a neutral plasma. This is a neutral gas. This is an electrified and magnetized plasma. So everywhere you see gas, think plasma. But this is the convection zone. So this is that area that we were talking about. It has all that craziness going on. Lots of bubbling. Just like a cauldron bubbling or a pot of water, and you see all the bubbles and stuff rising from the bottom. That's kind of what they're trying to show here. But when you have those, remember those toroidal field lines that are being lifted up by some of these buoyant processes, they rise and pop up through the surface and then go back down. But they're coherent. And remember how we talked about how the particles are jailed by the field? That these are kind of like jail bars. The particles can't pass, they can't get out. They can't escape. Well, that's exactly right. The X's here are showing that all of this plasma that's trying to bubble up to the surface, and this is how you get brightness out in the convection zone, is this stuff bubbles up to the surface and you get energy out. When you cross, or when you come across one of these tightly wound lines, or field line configurations, what we call flux tubes, suddenly it breaks the ability of that plasma to get past it. It can't get out. So inside this flux tube, because this is actually not just lines, but it's actually a tube, kind of like those solar slinkies we were talking about a little while ago, you know, at one of the previous mini courses. These tubes then prevent that hot plasma, that energy, to enter. And as they pop out of the surface of the sun, that's why it's dark, because it's preventing the convection from doing its job in these regions. And again, same thing here. It's preventing the convection. Does that make sense, hopefully? So you'll get brightness all the way around, but you won't get brightness in the sunspot. And we'll talk a little bit about the umbra and penumbra next. So hopefully you see hopefully that was clear. So let's talk even more about this. So we have sunspots, the umbra and penumbra. I'm sure you've heard people talk about it. The umbra and penumbra, it's not just for sunspots. I mean, this is for shadows when it comes to shadows. The umbra is the darkest part. The penumbra is less shadowed. So if you can actually look it up just in terms of how things are shadowed, like the way the sun shines on the earth. And if you don't have a point source, you can actually get a penumbra where it's not quite as dark, it's not quite as eclipsed as the umbra is. And so they took that concept and they applied the same kind of concept to sunspots. So the core of this thing is called the umbra, okay? And the average size of this thing is about 1,000 or 10,000 kilometers. But it can be, or 1,000, well, it says average size is 10,000, but it can be as big as 60,000 kilometers. We've had these sunspots be, you know, Earth-sized. It's pretty crazy how big these things can get. And a sunspot group in of itself, that's multiple sunspots together, like here, can be monstrous. I mean, unbelievably big. You know, bigger than Jupiter. You can put multiple planets in these things. So if you can see here for this one, this is a colored one, you can see there's the umbra here, the penumbra, which you see are the filaments, and you see it outlined here. The penumbra is the part that is, and I hope I'm pronouncing these words properly, the penumbra is the part that looks filamentary, but it's not quite as dark. And we'll talk about why that is in a moment. But it's still kind of shadowed. So this is always on the outside of the penumbra. Okay, the typical size is again about 5,000 kilometers. You can actually see waves that move across these, and solar physicists really study this kind of thing. BBSO is going to be doing that, or has already been doing that, because they can get incredibly good views. They have an optic that is part of the test product for DKIST, which is the amazing space telescope, DKIST. One of the amazing, ground-based telescopes that's going to be looking at features on the sun at resolutions we've never seen. And we can't wait. I think its first light for DKIST will be in 2020. And it's going to be stunning what we're going to be able to see. And we're going to be able to watch all sorts of little microprocesses coming through. Hopefully it's going to answer a lot of questions, both when it comes to sunspots and active regions, but also features in the corona. Anyway, okay, so you see that basic kind of concept. And then around the outside, do you see all these little kind of bubble parts? This is what I was talking about with a pot of boiling water. These are all the granules. These are all this part of the convection zone, everything bubbling up. And the neat part about this is that you can see bright parts and dark spots. The dark parts are where you're not getting as much convection. You're blocking the convection a little bit. The bright spots is when it's kind of a bit enhanced. And that becomes important when we talk about faculae, which we will in a minute. But let's continue talking. So then you can have sunspots with the umbra and the penumbra. It can be very simple, or they can be complicated where you have sunspot groups. It can get very complicated, which becomes a big challenge for scientists as they try to classify what regions are what, how they take these images apart to try to understand the dynamics of them. So what happens under the surface? So now let's take, this is an artist rendition. I love this one. And I've got a link right here to, if you want to see the source of this, by Thomas in 2010. I thought this was a really neat kind of drawing because it just looked so otherworldly. So what you're looking at really is the surface of the sun. Remember seeing those little pockets? These are those little bubble things that are bubbling up to the surface. And then this is the magnetic field. This is the flux tube. Remember I was talking about it being kind of like a slinky? Well, the field lines in this area are straight, and so they're going to come out from underneath the surface of the sun, which is this area here. They're coming out from the surface, and you're seeing a bunch of pore holes, but they're actual field lines. They just chopped the field lines off so you could kind of see into this structure a little bit. And so right coming out of the sunspots, they're very, very, very straight field, and this goes up into a magnetic loop. So this is one part of the sunspot. And this recessed area you can see in here, this kind of crater, this is where the umbra is, okay? This is why it's super dark. Nothing gets through this. You can see this is if this were a jail, I would dare anybody to try to get out through this. This looks like a bamboo, nightmare trying to get through this. Now, if you go to this outside rim, do you see this outside rim? It's kind of raised a little bit. You're showing the field kind of bending and folding over. And you're seeing that some of that field actually pops back down under the surface and down underneath. You can see it here too. It folds up and then pops back down, right? Well, this is the penumbra region. And the reason why it's not quite as dark is because it's not impenetrable like this. Some of those field lines actually come out, and so you can get a little bit of convection. You can get a little bit of stuff popping up from the lower convection zone up to the surface, but not a lot. Just a little bit. So it's not going to be as bright as the surface of the sun, but it's going to be brighter than the umbra. And that's why it looks like this. So in this region, the field lines are coming straight out. That's where the big bundle, the bamboo bundle of stuff is coming straight out to make those loops. This is where the field is kind of folding back down, kind of coming out a little bit. Some convection gets through, some light is able to escape because the convection cells are able to push stuff to the surface, but just not as much as out here. So hopefully that gives you an idea of why you have an umbra and a penumbra looking the way they do. Okay? So with that in mind, we have tons of ways of classifying sunspots. We have sunspot groups, and I'm going to talk very briefly. Oh shoot, this cut that off. That's too bad. I'm going to talk very briefly about the Mount Wilson sunspot group classifications because it's the ones that you probably will see most often in public websites that cater to just ordinary folk trying to understand what in the world these things are and what ones are dangerous and what ones aren't. Now, I'm not going to go through all of this. What I've actually done is I've got a link here, and I'll put this also in Patreon to talk about, or to give you an idea of where to go. I like Space Weather Live. There's definitely colleagues of ours, and I think they've got a great example talking about all the different types. You have alpha, you have alpha P, alpha F, you have beta, you have beta P, you have beta F, you have beta gamma, you have gamma, and then you can add delta groups to them. I mean, so basically, you can get a really complex group that looks like, here's a beta, gamma, delta sunspot group. This is a very complicated group. Like I said, I'm not going to go through all of this because a lot of this is academic, but it gives you an idea now because here's a simple classification rule from Mount Wilson. You should be able to understand this now a bit better because we talk about spots of opposite polarity. You can see red and blue. Those are opposite polarities. Here you can't really see that, but you can see that in the magnetogram. This is the white light image, and this is the magnetogram image of false color, obviously, of the magnetic field. And this is the same sunspot group. So you can tell they look very different, but not really. You can see the big part here. You can see this spot here. You can see these two. You would never know from this that they had opposite polarities, but you can see it right away from here. Again, you don't realize that these have opposite polarities, but they do. And so this becomes very dangerous. We call these delta spots. And the reason why is because they have spots in umbra, meaning the dark spots, of opposite polarity. They're together in a single penumbra. So you can look at that and see, okay, is the slightly darker area contain a single color, or does it have double, two different colors? And in this case, this area here has in a single penumbra, the slightly darker part, not the really dark part, but there are two polarities in there. So immediately it becomes something where you can have a delta in there. Okay, so that's what this sunspot group is, and you can learn a little bit more about them. How much that is going to help you understand what's a dangerous sunspot or what is a flare-producing sunspot group is debatable. Most of the time you can just take a look at some of the color images or even the black and white images of the magnetograms, and if you see a lot of color mixing, that's bad. So this was definitely, it could easily have been an X-flare producer. It probably was. I forget which group it was. But this is the nice example that Space Weather Live has on their website. And I like I said, I will put this link up on Patreon for everybody to see. So you guys can definitely go there and check it out. Okay. So let's talk a little bit about why sunspots are visibly dark, but they're radio loud. People often ask me, well, if sunspots are so dark, then how can we care about them in terms of solar flux? Well, we care about them because they're very active, and we care about them for other reasons, and I'll get to another reason in a minute. But the reason why there's so much confusing information about sunspots is because it depends upon the frequency of light that you're looking at. So for example, here's an example of this sunspot group back in 2003. And this is solar irradiance, so this is essentially solar flux. And they're like looking at the sun, and there's not much change in the solar flux, and then suddenly, boom, there's a huge decrease. Now, 0.34% is not a big decrease to most of us, but it's pretty big considering this was just one tiny sunspot. And that's because it's dark, right? So when people say, well, sunspots are why solar flux happens. Well, no. Sunspots actually don't increase solar flux, not the sunspots themselves. Certain aspects around them do, but not necessarily sunspots. Sunspots themselves can be indicative of other things. That's why you can use them oftentimes as a proxy for solar flux and brightness and things like that. But actually inside a sunspot, the visible light, the solar radiance goes down. And this was observed by the TIM radiometer on the source satellite. So you can get this from a NASA website if you want to take a look. But here is a 14 gigahertz image of the sun by the Very Large Radio Array called VLA. This is a telescope array on the ground. It's huge. And it shows, if you notice what it's showing, you can kind of see the outline of the sun. It's pretty dim. But look at all this. Look at all these spots, right? You know what those are, right? They're sunspots. They're sunspot groups. So you can have the same sunspots be dim visibly, but in radio noise they can be extremely high or extremely loud. And as a matter of fact, you can see many of them. The brightest parts of that radio noise come from the center of them. It comes literally from the center, from the umbra. Here's a view, a similar view. This is from TRACE, and this is showing, they're looking at the edge of the sun. So this dim region right here, this is a sunspot. This is the umbra of a sunspot. And TRACE shows for 8 gigahertz, they're showing a radio noise, a radio source, literally right above it. So it's not right at the sunspot itself. If I go back here to this picture, it's not right here where the radio noise is happening. It's actually out here. There's radio noise occurring out above in those magnetic loops. And it has to do with gyro resonance. It has to do with the third harmonic. It has to do with lots of stuff that, this is way beyond the scope of this. And they're still trying to understand and really detect it to the degree they want to. But you can imagine it gets to be extremely tough when you're using arrays that measuring 14 gigahertz, that's one frequency of light, 8 gigahertz, there's another frequency of light. You're talking about irradiance in visible range, which is, radically different. I mean, you're talking about much higher frequencies. So, it's hard to kind of overlay these types of observations on top of one another. And we'll talk a little bit more about that when it comes to the telescope part. So, if sunspots are so dim, why does solar flux go up when the sun is active? Well, that actually has a hidden source. And it's not hidden to those who know, but it's hidden pretty much to the general public because For some reason, the general public just doesn't know anything about faculae. Facula and faculae. The plural is faculae. I still get it wrong. I still call it facula all the time, even though there's more of them. Anytime you look at, let's say, an H-alpha image of the sun or a calcium line, you see these bright regions. Usually they're around sunspots. You can see a lot of them that are nearby sunspots, but there's these bright regions in here. These are the faculae. That's where the solar flux comes from, not the dark sunspot, right? The bright stuff. Here's a close-up picture of the bright stuff. Look at these. Look at the faculae. See how bright? See how dark? But around the sunspot, you almost always have these faculae. And so that's where the solar flux comes from, and this is why we can use sunspots as a proxy for solar flux, because oftentimes the more sunspots you have, the more faculae you have. So this is why there's so much confusion, is because a lot of things on the sun, just like solar transient phenomena, a lot of things on the sun are connected, and we often have to use proxies. And so we say, well, this is associated with this parameter. It doesn't mean it causes it. But it does mean we can use this particular parameter as a proxy for measuring something else. Unfortunately, what happens then is a lot of people end up connecting the two, thinking, oh, this causes this. No, 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 no. That's not how it works. So this is the hidden source of solar flux. So for all you amateur radio operators and shortwave responders out there, yes, sunspots are a proxy for solar flux, but they are not the cause. And so when you think, my gosh, I'm going crazy because sunspots are dark, how can they be a source of solar flux? And on top of that, then, you know, why do we get radio noise from them? And how does all that work? This is why. The problem is that we've got faculae, so we've got things that are being confused for other things. You know, the bright regions are being confused for the dim regions because they're always associated. And we've got different frequencies of light that have different features with sunspots. Sunspots will be visibly dark, but they'll be radio bright. So there's a lot of complications, and we have to be very, very careful when, as physicists, that when we talk about this stuff, we're very precise with our words, and we're very precise with the types of measurements, and we don't get them mixed up. Because trust me, I've gotten them mixed up more times than I can count, and sometimes I've had to go all the way back and relearn and unlearn everything I learned, because I learned something wrong at the very beginning, and I built on that, only to come up to a brick wall and say, well, wait a minute, this doesn't make any sense anymore. So I have to go unlearn all that stuff and go, oh, gosh, I screwed up my frequencies. I screwed up the light, you know, that I was looking at, and made an assumption I shouldn't have, and ran with it. And this is why people get into trouble so often with this stuff. Here's an example. You guys are familiar with the butterfly diagram, right? I just showed you one, but actually showed the sunspots going down. Faculae, obviously, because they're associated with sunspots, they also have a butterfly diagram, but it's slightly different. And that's what you're looking at here. You recognize it? See the butterfly coming down? This resolution of this image isn't very good, but it's 60, oh geez, 50, 60, 70, 1980, 1990, 2000, I think that's what it is. And what you're looking at, solar faculae observed at NAOJ in Bitaka. This is the northern hemisphere, and you're seeing peaks. But you're seeing peaks that seem to be off. That seem to be off of where the butterfly diagram is. Well, and there's a reason for that. This is the southern hemisphere, again, peaks, okay? And there's a reason for that. The reason for that is because they're not actually looking at just the faculae that is associated with sunspots. There's another kind, okay? I say right here. Many, but not all faculae are seen around sunspots. The ones that are exhibit the same butterfly diagram as sunspots do. But you notice the brightness up at the poles? See the brightness at the poles? You notice that they come, if this is the beginning of a sunspot cycle, so a new solar cycle, and this is the end of it, this is solar minimum, right? This is solar minimum. Another solar minimum here, another solar minimum here. That's where these peaks are. They're at the solar minimums. Why? Because that's when the polar faculae maximize. So these polar faculae are very numerous, are most numerous at the minimum of sunspot activity. So the nice thing is that really the source of solar flux, a lot of solar flux, actually doesn't completely disappear at solar minimum, even though all the sunspots do. So for those of you who've said, well, when the sunspots go away, how come there's still some solar flux? Why doesn't solar flux go even lower? Well, this is why. Again, sunspots are not the source of solar flux. The faculae are. But the faculae aren't only around sunspots. They are also disassociated. There's also a bit of faculae all the way around the sun all the time. So the brightness never totally goes away. So even at solar minimum, we may struggle with amateur radio and shortwave radio because we don't have that much solar flux. But there's always going to be some, and at least at solar minimum, the polar faculae help. They help immensely. Okay, so now I'm going to get to how to view such a complex star, right? Because we've had a lot of time. I'm going to take a sip of water here if you don't mind. We've had a lot of time talking about all these different aspects of what sunspots are, just even something as simple as a sunspot. You'd think, my gosh, it's just a spot on the sun. How could it be so complicated? Well, you see that it's driven by the dynamo. You see that it's driven, that even just having a sunspot emerge off of the solar, through the solar surface is a very complicated process, part of it which we don't even understand yet. We definitely don't even really understand how the magnetic field flips at the end of a solar cycle and starts a different polarity, the opposite polarity, for the next cycle. All of that is still being understood. But we have some picture of it. Yet in order to get that picture, we have had to look at the sun from many different frequencies using many different telescopes. There's all sorts of ways we can look at the sun, and then we got to try to piece that picture together of all the different layers and everything else that we're looking at to try to understand really what the physics is and marry the mechanisms that we think we see. Okay, and so that's what the next part of this topic is. And I don't have that much more to go, so don't worry. I'm not going to go as long as I did last time. But I think I'll stop for just a second to see if there are other questions. And hopefully this is continuing to update. Let's see. I tried to read of solar seismology and my brain hurt. Yes. Yes, it's oftentimes very, very difficult, very... Helioseismology is a fascinating subject, but oh, it's so difficult. These are areas of the sun. When we do helioseismology, the neat thing about helioseismology is that the sun, just like the earth, can ring like a bell. And there are sunquakes, not just earthquakes. We have them on the surface, but because of the sun's unique nature, the interior of the sun is where we have the convection zone and all that kind of stuff. And it's a liquid, not a gas or not a solid. There are lots of processes and resonant modes inside the sun that are occurring all the time. And we can sound them. We can ping them and hear, in a sense, listen to the sun. The problem is that our techniques are not, not super great. And a lot of times the things that we get are not completely repeatable. It's still a very new, I want to say a new art because we've been trying it for a long time. But it's just a very difficult thing to do. And the insights that helioseismology give us are amazing because there are precursors to solar cycles that actually can happen 20, 25, 30 years in advance. So some of the things that we've seen with helioseismology that are repeatable can actually tell us what the sun's going to do 30 years from now. Can you imagine? That's how long some of these processes take to really manifest up at the surface and drive things like space weather. The sun is just a fascinating creature, but we just don't understand everything it does yet. So yes, you're not the only one whose brain hurts with helioseismology. Mine does too, and I don't pretend to understand it very much. Okay, so how to view such a complex star? Well, as we know, our sun is this giant fusion reactor that is driving space weather. We've spent a lot of time on sunspots. Here's an example of how small the Earth is compared to a sunspot, or a sunspot group, and just the umbra. I mean, it could fit basically in the umbra of that sunspot. And we have energy output in the form of electromagnetic radiation from X-rays all the way through radio waves. We have solar wind plasma and magnetic fields. We have flares. energetic particles that what I oftentimes call solar radiation storms, coronal mass ejections, what I oftentimes call solar storms. And we have to be able to look at this sun and see all these different bits of information all at the same time and try to put it together in a big cohesive picture. And it's very difficult. So really, we kind of take a look at the sun and peel those layers we talked about, kind of peel them like an onion. And oftentimes we have to use space telescopes to do that. We do it to some degree on the ground, and I'll tell you why ground imaging is limited compared to space telescopes. But let me just give you an idea. Here is one segment of images in different wavelengths, okay, different energies, different temperatures. It's all interchangeable, and I'll tell you why in a minute. But this was all taken at the same time. Can you believe that? Look how radically different our star looks in these different images, but it's all the same moment in time, essentially. When you get, here's the white light, you can see the sunspots. This is what we see with our naked eye. You go up a little bit higher, you can actually see a little bit of the faculae that we were talking about, and you can also see when there's solar flares, you can actually see like electrical, almost like lightning going across, connecting these regions. You go a little bit higher, this is 304 angstroms. Our red sun, now you're looking at ultraviolet. Well, this is ultraviolet too, but you can see the transition region. Here's the chromosphere, and here's a loop from a coronal mass ejection, or what we call a solar storm. Here's a little bit higher, 211 angstroms. You don't really see the coronal mass ejection nearly as well, the loops, but you see more of the tenuous atmosphere, and you also can see coronal holes. Guess what? You don't see the coronal hole there, do you? That's because coronal hole isn't really a hole. It just doesn't emit in this energy at this temperature, so it seems dark. But that doesn't mean that there's not energy there, that it's really a hole. We just call it a hole because that's what it looks like. So there's no real holes on the sun. Don't worry about that. Anybody tries to tell you that, that's crazy. Here's 171 angstroms. Now you can actually see magnetic loops much more cleanly. You can actually see blast waves on the sun. It's very cool. And then you get even higher. Here's 131 angstroms. This is actually the hottest part of the flares. You can see how hot the sunspots or the active regions look. And so you get the hottest material coming out during these eruptions. So the scientists look at these different color codes, and immediately we know what frequency of light we're looking at, what part of the solar corona we're looking at, and what we would see in, you know, if we wanted to see the details of a solar flare, we would go to 131 or even 94 angstroms. If we wanted to see, you know, the blast wave of the shock wave propagating across the surface of the sun during a flare, we would go probably to 171, maybe even 211 or 193. There are certain wavelengths that are much better, certain temperatures that are much better for seeing certain things because they're looking at particular layers, basically, in the solar atmosphere. Remember, the solar atmosphere heats up quite a bit. So how do we get so many views? Well, really, it has to do with spectral lines. Here's an example of a solar spectrum from 4,300 to 4,400 angstroms. This is essentially visible blue light. You can actually see this light. See all the dark lines? These are all what we call absorption lines. These are because we have so many different elements. There are like 67 different elements present in the sun. All of these elements are being bombarded with energy all the time, and so they have electrons that are being promoted, kind of like, because it's a plasma, the sun is like a big neon beer sign. It's a big mercury lamp. You're exciting it, you're promoting what we call promoting electrons to a higher energy state. They have to get rid of that energy, and they emit it in a color of light, okay, in an energy of light. That's what these absorption lines are, okay, so look at all the choices. Every time you see black, these are the choices. Here's what we call the H gamma line. You guys have heard of H alpha. There's an H alpha, H beta, H gamma. That's what this one is, and an H delta. Those are all in the visible range. H alpha is red. H gamma is blue. I think H beta is, I think it's green. It's either green or yellow. And so we use these different spectral lines to image the sun. So we're looking at the emission of energy from one element in the sun that's being heated up, and blah, it's spitting out energy but it only shows what that element is doing, where it's you know, where it is in the sun and where it's being energized. But by doing that, we are able to look at the sun in very unique ways and see what's going on in different layers and see what's going on in different phenomena. Okay? Now, hydrogen, of course, is the lightest and most abundant of the elements, followed by helium. But spectral lines from even very heavy elements like iron are useful for imaging. And as a matter of fact, I'll show you that. We use iron quite a bit for imaging. And of course, spectral lines only tell us about the part of the sun that forms them. But if you choose them carefully, these are thought to be representative of the majority of the sun. So scientists have taken a lot of care to choose all the different types of lines that they use. Now, granted, these are false color images, so we've colored them. That's not really what they look like. The images come out in like a black and white because we're looking at different energy levels. But it's just essentially gradients. It's just essentially how bright is it? It goes from totally bright to, you know, dim, completely dim or not black, you know, nothing. So we then color them and color code them. They don't really emit in these visible colors because it's the wrong wavelength. But they still create these images when we do a full disk. Now, a couple of these, I've got the HMI. This is the magnetic imager. You've got a Dopplergram that actually shows magnetic fields and moving back and forth. It tells us a lot about the processes on the surface. We also have magnetic field polarity. This is where we get the polarity for the sunspots to tell how complicated they are. These are slightly different imagers because they're imaging the magnetic field directly. HMI continuum, this matches the visible light photosphere, which is what you see here, which is a 450 angstrom image. That corresponds to 6,000 degrees Kelvin. But you go into UV, into the ultraviolet, you can get 1700. There's again, you can see the faculty. This is 1600, which is really close. There's the 304 I told you about, 171. All of these have different temperatures associated with them. You go into 193, you're now getting into the corona, and you can see it's 1,000,000 degrees Kelvin. Again, here's 2,000,000 degrees Kelvin in the hot corona. Here's 2.5 million degrees at 335 angstroms, 6 million degrees Kelvin, that's 94 angstroms, and 10 million degrees Kelvin. So we are imaging all these different things, and we're using different spectral lines to do it. And if you really want to know the details, and this is Karen Fox put this together, I was really appreciative. Here's the Dopplergram, magnetogram, HMI. I'm not going to go through all of this, but look what you can see with some of these. Here's a calcium or carbon 4 line. This one's helium 2. This one's iron 9, iron 11, iron 14. Didn't I tell you we use iron a lot? Iron 16, iron 18, iron 20, iron 23. This is what we use for a lot of these, for the extreme ultraviolet images that you see. And this is all AIA. This is all the stuff you see from SDO that give those beautiful images. Most of them are just different emission lines from iron. Isn't that amazing? So that's how we do it. And that tells us a lot about what is going on in different regions, in different and with these using these different elements, because they're all emitting light. But they're all emitting light just slightly differently and in different areas. And so here I did it again in a slightly more simplified method. And I think I've already gone over most of this, but you can see if you want to pause, you know, once this is up on YouTube, if you want to pause and read this, I'll kind of step away for a second so you can get a nice freeze frame without me in the way if you want to read this. This is a much more, I guess, readable and livable version of the slide I just showed you that gives you a description of kind of where the layers are and how we as solar space physicists and solar physicists actually use the AIA imagery to get an idea of what's going on in the sun and why we look at certain colors. So why do we need space telescopes? And I'm getting really close to the end here, so I've only got a couple more slides, so I think time-wise we're doing okay. Maybe I'll pause one more second and see what you guys are asking, if you're asking questions. Let's see. Are any new theories, boy, Susan, I'm only getting you. Are any new theories arising from recent USA total solar eclipse data? Oh, yeah. Yeah, actually, yeah, and I got to be careful because there's some proprietary stuff that yeah, we're analyzing eclipse data like crazy, especially with DKIST. There are some, because we have this solar eclipse that we just had, and we have another one coming up in 2024, and there's a lot of solar eclipses all over the globe quite frequently. And so we actually, if we're able to chase an eclipse over a long stretch over the ground, we actually can install multiple telescopes at different facilities and watch the eclipse over, a longer period of time. And the neat thing about that is that because we can use ground-based telescopes to see the corona, we can see things that we oftentimes can't see when there isn't an eclipse. You can actually you can make images and take advantage of some imagery that you wouldn't normally be able to do. And so a lot of people are using the eclipse and studying the corona and what's going on in the corona as a precursor for DKIST, partially because DKIST is going to, even though it has very high resolution, it's not going to be able to image the entire corona all at once. When you have high resolution, it's great because you can see things in great detail, but your field of view shrinks quite dramatically. And so if DKIST wants to make a really big mosaic or a big picture, it has to do tiny little images in move and then take another shot, and move and then take another shot, and then piece them together in a mosaic. And that takes time. And that's not as useful as if you could just take one snapshot in time. So we're using eclipse. A lot of people in the field, especially, for instance, Dr. Shadia Habal, who I know and I love her to death. She's very savvy when it comes to eclipse measurements, and she's published so many papers, her and her team, on eclipse measurements. And the amount of the fidelity that she's gotten and the usefulness she's gotten out of doing analyses of the corona during eclipses is just fantastic. So yes, to answer your question in a long-winded fashion, we are using eclipse data to try to tell DKIST where it needs to point and what it needs to be looking for and how it needs to be analyzing the data that it's going to be getting. So they've become almost indispensable for some solar physicists working in a certain type in a certain discipline, looking at the corona and looking at especially some of the transitory nature of the stuff that comes off of the corona. So it's very, 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 very useful, and I'm very grateful that we can do that. And that's actually a good segue, because why do we need space telescopes? Even though we can do this stuff from the ground to some degree, there are limitations to what ground telescopes can do. And what I've got here on the top here is a picture, a diagram of basically what we call the atmospheric opacity. You can see from 0 to 100% of the different frequencies of light. Now, visible light, they show this cute little rainbow right here, and I've got it locked in to this bottom picture as well, where it breaks things down a bit more. But here's that visible light window right here. And you can see you have 100% opacity when it comes to very, very, very energetic wavelengths of light. So this is gamma rays, X-rays, and ultraviolet light, oftentimes what we call EUV. So all of those beautiful images we see with the Solar Dynamics Telescope that people say, oh, this isn't real, it's CGI, there's no way, I've never seen anything like that, no ground telescope can replicate it, therefore it must be fake. No, we have an atmosphere, and that atmosphere prevents us from seeing that light. It absorbs it all. So even though that light is raining down on Earth, you have to get above the atmosphere in order to see it. So that's why we have space telescopes. So all the YOCO instrumentation, the SDOs, the stereos, the EIT, the SOHO, all of this stuff, we call it EUV typically. EUVI is the one on stereo. EIT is the one on SOHO. SDO has AIA, and it's all EUV, extreme ultraviolet light. These are the iron lines, typically, that we look at and we look for. We cannot see them here on the ground. The visible window, as you can see, the opacity drops down right at where visible light starts. This answers that other question where we were talking about, well, why do our eyes see what they see? Well, because the opacity of the atmosphere is pretty thin here. And this is where our eyes have decided, hey, this is a good area for us to be able to pick up light and see our surroundings. Why don't we have X-ray eyes? Well, because the sun doesn't light it up. It'd be dark. If we could see X-rays, it wouldn't make a difference because they don't get down here. We'd have to go up in space and then we'd be blinded because there'd be so much of it. But down here on the surface of the Earth, we don't need X-ray vision because it doesn't come through from the sun. Or ultraviolet. That's why we don't really see an extreme ultraviolet. Now, some ultraviolet gets through. That's what the birds and the bees, you know, some insects see in ultraviolet. You get some of that, but it's a very, you know, purple edge of this region here. And then it kind of gets a little bit opaque here and there. There's some atmospheric, you know, distortion and issues. It depends, very space weather related. But, you know, this window kind of closes. And then, you know, so we get some infrared. This is what heats our planet. You can see infrared wavelengths here. But then you go into microwaves. Once again, you get to there's a closed window in here where it's between low infrared and microwave, the high end of microwave. It then falls back down, so you do get some microwave radiation that reaches the Earth. This is what we call the radio window. So you've got the visible window and the radio window. And that starts, you know, right about where the VLA telescope starts. You know, you're 15 gigahertz, somewhere in there. So it's around there. You can see it kind of wiggles again. It's a soft boundary. But then you're open, completely open, all through television, all through shortwave radio. And as you start going into the broadcast bands, once again, it closes back. You get the atmosphere becomes opaque. So that's one of the reasons why when you're listening to FM radio, a solar flare happens and you don't hear it. Well, you're being protected once again by the atmosphere. Now, that doesn't help a lot of the amateur radio operators and some of the other bands, especially when you're trying to communicate to Earth, because space weather affects these windows to some degree. And so these are not hard boundaries. But for the most part, you have a radio band in here that really gets decimated during things like solar flares, because all that noise can actually reach Earth, just like all the light when you're here in the visible range. So hopefully that explains a little bit of that, why we have to image. If we're going to do a ground telescope, we have to image here, or image in this window. We can't image X-rays from the ground. We can't image extreme ultraviolet from the ground. We just can't do it because it would be dark. We'd see nothing. We can build the imager, point it up, and all we'd be staring at is a black image because nothing gets through. So really, when we talk about telescopes, and this is a second to last slide, so we're almost done. When we talk about space telescopes, really what we need to be thinking about is, and especially when it comes to scientists and the science that we do and how fast can we do it and how accurate can things be and why does it seem like scientists are wishy-washy when it comes to this, that, and the other, and things should be cut and dried and easy. Well, nothing is easy. As one of my colleagues says, if it were easy, everybody'd do it. And I think he hit it right on the head because solar physics and imaging the sun is not easy by any stretch. First of all, we have different images. This is different images in wavelength of the sun at the same time. Look how radically different they are. These are two images from SOHO. This is EIT in 195 angstroms. This is 304 angstroms. Try to overlay those and get them right. You know, even the boundary, the edges of the sun is not the same. So you say, okay, well, we'll just match up the perimeter of the sun and you know, like right hand, left hand, just overlay them on top of each other. Well, what if one hand is slightly bigger than the other? How do you overlay? How do you match it? It's not so easy because you're not really looking at exactly the same things. So some of the scientists that are trying to do this, the solar physicists who are courageous enough to do this type of work, they're desperately trying to put pieces together that are not necessarily easy to put together. So that's part of the problem. Look at this, for instance, in Yoko. This is X-rays, and again, you're getting even a softer boundary in certain areas, and you're lighting up different areas completely. But these three images, you wouldn't even tell that's the same sun, right? And then here we go. Here's the VLA we talked about again in like, I don't know, 14 gigahertz or something. I'd have to translate 91 centimeters into a frequency. But you're getting radio noise from two very bright spots here. But the edge of the sun, they even had to write the edge of the sun on, because the imagery that they get there, you can't even see the edge of the sun. So again, how do you overlay these and say it's all the same sun? And then how do you marry the mechanics and the properties of the mechanisms, the physical mechanisms that are happening when you're looking at so radically different frequencies of light that may or may not overlay properly? So wavelength differences, that's one of the biggest things that we deal with. But there's another one, and people don't appreciate this either. Telemetry differences. Here's an example. I just took these images off the web just yesterday. This is October 27th, so it's actually today, but it was last night when I did it. You know, I'm in the tail end of the time zone, so it was still the 26th when I did it, but UTC was already the 27th. So here's SDO. Here's 193 angstroms for the AIA image. Here is the beacon image from stereo at the same time. Now, we're not looking at the same sun. This is the back side of the sun. This is the front side of the sun. But we are looking at almost the same wavelength, 195 versus 193. But hopefully you can see this with the camera. The resolution of this image is fantastic. It's beautiful, right? The resolution of this is poop. Our beacon images are absolute poop, and we know that. But the reason why they're poop is because we are trying in real time to send a signal from basically behind the sun all the way back to Earth. And if you think of telemetry being like a straw stuck in a soda can, the bigger the straw, the more soda you can suck very easily. If you have a tiny thin straw, you can suck really hard, but you're not going to get much out of it very fast. And that's what we're talking about. The pipe that SDO has is huge. We get gigabytes of data down a day, maybe more. And SDO, as a matter of fact, that's the reason why SDO is parked in an Earth orbit. It's not parked where SOHO is. SOHO's sitting out in front of Earth. That's why you never see it being eclipsed by the moon. But SDO, you see the moon passing between the spacecraft and the sun all the time. And you think, well, that's stupid. Why would they do that? The reason why we did that is because we needed a big straw. We wanted to get down very high fidelity images at very fast cadences, meaning rapid fire. We wanted to get them down fast and get them high resolution. And the only way we could do that, park the satellite very close to Earth so we can get a big straw and suck down that data fast. Otherwise, we'd never get it down. Stereo, on the other hand, is using one of those little cocktail straws. You know, those little tiny things? It's so far away. We can't get much data down in real time. Now, granted, we can get better data down if we take our time. But this is beacon data. This is the data that we try to do in real time so that we have some forecasting capability. Believe it or not, stereo was never really designed to be an operational satellite used for forecasting. But the scientists were so savvy, and they wanted to be good to NOAA and everybody who's doing space weather forecasting, that they ensured that they had beacon data that was lower quality data, but at least it gave us images of the sun that are good enough for us to do forecasting with. So if we ever lose stereo, we're in trouble. But this is a science mission. This was never meant to be an operational forecasting mission. And I'm hoping we can change that. We need to get some operational satellites with NOAA, the Air Force, and other agencies to get something up there that isn't a science telescope, but is rather one that's supposed to be up 24/7, so that if we ever lose stereo, we'll have something to replace it. Because if we lose stereo, we have no eyes on the back of the sun. So it's kind of sad. But at any rate, here's the beacon data. Now let me show you this. That's stereo data too. It's not beacon. So this is how good the telescope looks and the data looks once we get the full data down. Isn't that great? It looks as good as SDO. But it takes a while for that data to come down. We can't get it in real time because our pipe is so small. So going back to this, if I ever hear anybody say, and I've heard it many times, oh, stereo, well, its images aren't so good because it's kind of old. It's an old spacecraft, and you know, it's not doing so well. No, SOHO is old. We've kept SOHO alive far beyond its shelf life. This spacecraft is older than my daughter. But stereo's not that old. As a matter of fact, stereo is not really much older than SDO is. It's the telemetry that makes the difference. And again, you can see it's got really good imagery, but we have to wait for it. So that's really where I am, where we are. That's pretty much all I have to talk about today. So I will, again, go and see if anyone has any questions. I don't think my thing is updating as much as it should, but that's probably because I'm online. But let's see, okay. Can you give us any more info regarding your ideas to provide space weather updates on the nightly news? Oh wow, okay. That's neat. I'm glad, I appreciate you asking that question. Yeah, I am working on a course with, I'm working on some course materials for Millersville University. We are actually trying to create the precedent for a space weather certification that terrestrial meteorologists can take a set of online courses and actually get a online certification saying that they are a space weather broadcaster. And so we are working on that right now. We are beginning to develop the courses. I've got the, if I go back to, well, I won't push that too. But I've got the steering committee that I'm working on it on Patreon. We actually are doing some serious work on that, and they're helping create, they're helping me fill in the gaps when it comes to space weather users. So if you are super excited about helping out and getting involved in helping us create a field of space weather broadcasting, and you have input that you would like to share, please come to Patreon and talk to me. Like I said, the steering committee, the VIPs that I call them, they are actively involved in helping create the whole concept of the user regime and how space weather affects people. And they're giving me anecdotal evidence of how things are being affected, and they're helping to kind of fill in the gaps of what we understand as being academically important compared to what we actually see in the real world. And I can always use more input when it comes to that. So yes, I can talk to you far more offline, and you can find out more about this on Patreon. But if we get this set up, and it may take a year or so to get set up, what we'd like to be able to do is then potentially migrate this to the American Meteorological Society and set a timeline for when we can actually have people adopt, or have the AMS adopt this as a part of the CBM credential. And I'm leading an ad hoc committee that's exploring this concept right now for the AMS. And really, I think we need to kind of pave the way by creating some of these certificate programs that allow people who have a meteorological degree to be able to get skilled in space weather as well. So they can take that with them to become station scientists, or they can actually take that with them when they actually talk about a solar storm on the news when there is one happening, and they don't call it the wrong thing, which, you know, unfortunately a lot of meteorologists do. So it's still in the early stages, and if you would like to get involved, please see me on Patreon, email me, tap me on Twitter, and I will tell you a lot more about it. So thank you for that very, very insightful comment. Okay, let's see. I'd like to see a segment someday on how to interpret the various solar indices and space weather measures with regards to radio propagation conditions. Yeah, so I can do that. I can actually, we can dive into one that has all about indices, what indices you can use and that would be helpful and what ones wouldn't be. I didn't include that in this mainly because I wanted to do one that was more about the phenomenology of sunspots and help people understand why they're just they're not easy to interpret because there's so many different things that they cause and so many different effects that they have. But yes, we can, and again, the mini course tier of people on Patreon, they're the ones that are sponsoring this, so they have the ultimate decision. And so if you are one of those mini course tier folks, ping me and we will chat, and I would absolutely love to be able to set up a course like that, and we can even talk about which indices are the most important, especially for radio amateurs, as well as aurora photographers, and really how they correlate with some of the phenomena that you see locally. Because some of the global indices that we use as space weather people, they're exactly that. They're global, and they're delayed in time, and they show effects that really don't appear or don't, they really aren't relevant for, you know, a certain locale. Because although space weather is a global phenomenon, there are local effects, just like terrestrial weather. You know, you can have areas that are far more impacted by one kind of space weather and areas that are far more impacted by some other kind. Or you can have an area that is far more impacted by, let's say if you have a solar storm, far more impacted by the beginning of the storm, but not so much by the end. Whereas you can have another latitude, let's say, that's far more impacted by the end of the storm than by the beginning. So again, it really is locale dependent. And I think I talked about that in one of my early mini courses. I talked a little bit as to why that is, and it has to do with how the Earth's magnetic field maps down to latitudes on Earth. The parts of the field that are hanging out in the solar wind are the ones that map to the highest latitudes at Earth, and the ones that are more protected underneath map to low latitudes. So there are definitely different effects that are latitude dependent. So that's and the indices reflect that. And yeah, there are different indices to talk about. So that's a good idea. Okay, any other questions? I think that's it, and I will then say thank you very much. Thanks to all the patrons that have supported this and made this a very fun subject to do. And definitely, you know, come ping me on Twitter if you have extra questions, or post them here on YouTube, and I will see if I can try to get to them. It may take me a little bit, but I'll get to them. And that's it, guys. So thank you so much, and I'll see you soon. Okay, let me turn this off. And okay, bye.